Good afternoon, everyone. Thank you so much for being here for this presentation. My name is Ravi DABRAL. I work with a company by the name of OCSiAl. And if you are thinking, what's that name? That is oxygen, carbon, silicon, aluminum. A little of Breaking Bad style name. We are Luxembourg headquartered multinational company spread all over the world, and we produced one molecule called as graphene nanotube. Through the next 20 to 25 minutes, I will share with you all of our commercial applications in composite. That means whatever I share here with you, all of those applications are on field right now. And by the end of this presentation, I hope you will be able to figure out for yourself how graphene nanotubes can contribute to your business and your formulations. So to start with the obvious question, what is a graphene tube? You take one atom thick sheet of carbon, just one atom thick, not two, not multiple, and you roll it into a tube of about 1.5 nanometer in diameter and 5 micron and higher in length. That is what you call as graphene nanotubes. And these graphene nanotubes have some very interesting properties. For example, they are one of the most electrically conductive known molecule. They are more than 100 times stronger than steel in the tensile direction. And since they are just one atom thick, they work at extremely low dosages because there is no dead weight in single-walled carbon nanotubes or graphene tubes. So the working dosage is ultra low. I'm talking about parts per million in some cases. All of these properties make graphene nanotube a universal additive, which you can put in a lot of polymers and get the properties of conductivity and mechanical reinforcement in some cases. Now, how to use nanotubes? If some of you, as I guess, have used graphene nanotubes or any kind of nanomaterial in your own lab, you would see it's not the easiest to disperse. So we give graphene nanotube in pre-dispersed form, and what has to be done is they have to be dispersed, graphene nanotubes have to be dispersed in the base polymers in such a way that they form their own 3D conductive network inside the polymers, thereby exhibiting their properties of reinforcement, electrical conductivity, so on and so forth. For composites particularly, in the last 10 years, we have been able to develop multiple applications. Once again, commercial applications I would like to emphasize. And to share one of these applications today, I have with me our partner collaborator, Romar-Voss. Let me introduce Mr. Tom, who would talk about one such application. Mr. Tom heads the R&D of Romar-Voss. To you, Tom.
Thank you, Ravi. And hello, everyone. I'm Tom. I'm going to tell you a little bit about why we use the graphene nanotubes, how we process them, our conductive product range, and a product made by our customer Verwater Composites. But first, a little introduction about Romar-Voss. Romar-Voss was founded in 1965. It's an independent and successful distributor and manufacturer of composite materials and floor systems. We are divided in 3 divisions. So the composites part for the composites materials such as resins, core materials, etc. The floor system part for manufacture of synthetic coating and floor systems. And since this year, the panel solutions, which we provide standard and customizable sandwich panels. So why are we choosing the nanotubes in our conductive products? First of all, as we may all know, the graphite has some negative effects on the chemical and mechanical properties of the final product. This is due to the high working load of graphite, approximately 20 to 25%. And this also causes some darkening effects of your final color, like you see on the right pictures, on the right side. And also when manufacturing the graphite into your products, it can cause some machine disconnection and a slippery floor. So that's why we are using the Graphene Nanotubes from OCSiAl for all our conductive product range. When it comes to processing those nanotubes, we do that, we use a non-dusting form called the tubal matrix. We do that in a two-steps process. In the first step, we kind of make a pre-mix so that the nanotubes are perfectly distributed through the whole product. The distribution we will check on a glass plate, like you see on the picture below, and see if there are non-lumps left. And if this is okay, we proceed to the second step, and the second step is just putting those pre-mixed nanotubes into our final product. Our conductive product range at Romar-Voss exists of the customizable Graphene vanilla ester resins and Graphene-based spray gel coats. For now, we only have them in the black and light gray. Some other benefits for those nanotubes is a full conductive range, the possibility of light colors, also the maintained chemical and mechanical properties, and some cost efficient. Here we see an example of the product made by Verwater Composites. These are storage tanks. These tanks will store some fuel additives with low flash points. The liner is equipped with a Graphene 470 with some nanotubes in it, and those nanotubes provide the transportation of possible sparks to the ground, so that the sparks don't ignite the fuel that's inside these tanks. So thank you. Ravi is now going to show you some other applications.
Thank you, Tom. Thank you. So Romar-Voss is a commercial company operating a commercial setup. That means they cannot disperse nanotube at nanoscale. Hence, for such customers, we provide a pre-dispersed solution of nanotube, which we call as matrix. When we give matrix in a particular carrier, you will be able to use it and disperse it with your own commercial setup, like Romar-Voss does. We have a wide range of matrices available for various kind of base polymers. Now let me share some more interesting cases with you. This is a case of a mold coat. Let me see if we can really see this application clearly. Do you see the sparks? The sparks are missing in the second one. So what is happening here is, after putting nanotubes in the mold coat or gel coat, while opening the mold, there would be no sparks. And as a result of which, the whole process is much more safer. The whole process is also fast. That means faster productivity and safer operations. Also, as you see, anything which is anti-static doesn't catch dust. That means you don't have to clean it as much. And if you don't have to clean your molds as much, they are likely to give higher life. So this is just one of the examples how nanotubes are adding value to mold coats. There are other applications like filament wound or hand layup composites. For example, pipes through which sometimes solvents flow. By using nanotube, you can make these pipes anti-static or conductive you can maintain or even enhance some base mechanical properties, and overall the production would be clean. Not like carbon, where everything becomes black, including the walls and the product. Another example here is anti-static pultruded and compressed composite. Mind you, these are the lowest cost composite being produced right now. And by adding extremely small dosage of nanotube, I am talking about to the tune of 50 parts per million, 100 parts per million, you can make these pultruded composites anti-static. Since you're adding such a low amount of nanotube, you can also add color to your parts. That means now you can have gray or yellow cable trays or gratings. Another example is SMC composites or junction boxes made up of these SMC composite, in which you would find extremely high gloss, conductive behavior, and popular industrial colors like gray color. One very important market for us is printing rollers, where conductivity is really, really important, since sometimes we use solvents to print. These printing rollers roll at an extremely high speed, and it's more and more important right now to have these rollers as conductive. With tubal nanotubes, it's possible to make extremely conductive rollers in a clean production and at the same time have color also on the surface. A little bit about our venture and our efforts in the EV segment. The bumper that you see here is a bumper which can be coated or painted inline. So by adding nanotubes into thermoplastics, you can make it as conductive as to be able to coat inline along with your other material parts. Similarly, for under the hood applications like nylon 6 application, it is possible to use nanotube, reduce your part thickness and overall part weight, and have reinforced parts. That means lightweighting with similar performance. For battery packs, nanotube give you a very unique property in battery packs. You can have a formulation which can be extremely fireproof or fire retardant. That means you can add a lot of fire retardant. You can add other functional materials and still have space enough to add nanotubes, since nanotubes are added in such a less amount. Since we are a European organization, we are extremely compliant about environment, health, and safety. We are the first and only graphene nanotube company which is REACH compliant to commercialize about 100 tons of these nanotubes in Europe. We also have EPA consent. And sustainability is at the core of our vision. That means most of the application we collaborate and work with are the application where we are promoting and advocating the less use of material. So doing better with less. Also, nanotube, because of their design, use much less energy than its conventional anti-static filters. We have a global footprint, so you would always find somebody from OCSiAl near you. Most of the time, it's a good thing. And if you have any other questions, please feel free to ask me now, or you are also most welcome to visit us at our booth. Thank you. Yeah. Any question? Yeah. Can you pass on the mic there? Thank you so much. I was starting to believe that my mic was not working and I went through the whole presentation.
Hello, Ravi. Can you hear me? Oh. Okay. Thank you for the nice presentation and congratulations for this all nice work. I have few questions regarding the material because The material you termed as a graphene nanotubes, they already exist in the similar way like carbon nanotubes. Then they are categorized as single wall, multi-wall carbon nanotubes. What is the difference between these two terminologies? Are they same or they are different materials?
Single wall and multi-wall, you asked, right?
No, the terminology, what is the difference? Why they are, you named them as a graphene nanotubes instead of carbon nanotubes?
Yes. So when we say graphene nanotubes, the name implies that there is only one atom of carbon in the wall, one atom thick sheet, sorry, of carbon in the wall. There are not multiple layers. It's like graphene but rolled into a tube.
But still it is a carbon nanotube,
It's a
single wall
it's-
carbon nanotubes.
Absolutely. It's a carbon nanotube, but it's a single walled carbon nanotube.
Okay, okay, very good. The second is what is the growing method? Is it a CVD method or you have developed some other patent for this development?
It's a modified patented method, and we produce nanotubes in bulk.
Okay.
That means right now we can produce about 70 tons of nanotube per year. That's our specialty. And by the conventional methods, as you mentioned, by CVD, you can only produce few grams or few kilograms per day. So we have a slightly different method, a patented method. I don't know much about it. It's very secret for me also. Yeah, but we can produce it in bulk, like 70 tons, and give the prices which are commercially feasible.
Okay. The last question, just a curiosity, not a very technical question. About the processing, the carbon nanotubes, because of their nature, of their morphology, like the fiber-like material, sometimes they improve viscosity of the material. So do you have some experience with this one, how you handle this problem?
Absolutely right. Any additive which has extremely high aspect ratio, that means extremely high length to diameter ratio, will give some viscosity enhancement. In case of single walled carbon nanotubes or tube-all, as our brand is, what you get is not a real viscosity increase, but a thixotropy, which is shear thinning behavior. Yes. So if you have an application in which there is already some pressure applied while making the formulation, it should be okay. It's not a problem. But if still, in some cases, if it is a problem, if you need a very smooth and a very large surface, we recommend the addition of some additives by which you can reduce the viscosity to its functional range.
Okay, thank you very much.
Most welcome. Anybody else? Any other questions? Please, one here.
Sure. Thank you for your presentation. I was curious about knowing how you make the surface conductive. If you add the graphene to a resin system, they don't necessarily stay on the surface to create a conductive path. Is there a trick to do that?
Right, it's a very relevant question. When graphene nanotubes are dispersed, they stay throughout the material matrix, surface volume everywhere. So we mix it at a stage and in a way that they are dispersed all throughout the matrix. It's like a 3D conductive network. So we don't keep them only on surface. As a result of which, they give their effect even after the surface is abraded. For example, in some application like tires or shoe soles, where the surface can be abraded with time, you won't lose graphene nanotubes conductivity because they would be in volume also. Is that the question you asked?
The experience that I have is you add the additives, but sometimes they behave like a semiconductor. So you have a path, or sometimes you don't have a path. The trick is, or my question is, how do we make sure that there is enough particles joining each other?
Understood. Understood. I'm sorry, because the volume is low here, I got your point, yeah. There is a threshold. There is a threshold after which nanotubes, if dispersed normally, would have all that conductive joint networks. Yeah? So we make sure to give the recommendation that you have to add nanotubes beyond that threshold. So after a while, nanotubes plateau. Their conductivities plateau. Yeah? So that threshold must be added to get its effect. And since the length to diameter ratio is extremely high, it's about 3,000 to 5,000. Yeah? That threshold, that connection between nanotubes happens at very, very low dosage. But below that dosage, if you go, it would be a problem, as you correctly mentioned.
And the threshold?
This depends upon a lot of things, but most importantly, the inherent conductivity of the polymer that you are putting it in, how you are mixing it, how you are making the final material out of it. Is it injection molding? It is hand layup? It is spray coating? Depends on that.
Thank you.
I guess I'm out of time. If there is any more question, please do visit us in F82, hall number 5. I thank you all for your attention.